So let's go ahead and get started. So we're going to talk about how to adjust for ACI 211 mix design, because as you know, admixtures and SCMs like fly ash were not used very much in the mix design process, because back in the late 80s when they wrote ACI 211, they didn't have as much admixture and fly ash and stuff. I think the words may be in there, but they didn't actually show them. So how do you incorporate that into your mixes? So typically, if you remember from our fly ash discussion, you're going to have a partial replacement of Portland cement. So again, it's by weight. So instead of having 100% Portland cement, you may have 20% fly ash and 80% Portland in your mix. You must know your specific gravity of your particular source of SCM. So fly ash can range from 2.0 all the way up, I think I've seen up to like 2.9 for the specific gravity. So, you know, in this class, I'll obviously give you those numbers, but it's important to realize they're not all the same. Specific gravities change with these materials. It's not like cement where it's 3.15. These are common replacement values for whether it's fly ash or slag or silica fume. We will do a lab here in a few weeks where we actually replace a certain amount of fly ash and a certain amount of slag and a certain amount of silica fume. So we'll make some different mixes. It'll be kind of cool to make them and see how they change the workability properties and also the strengths. So let's kind of do a mix design to kind of incorporate it. So how does this all work, Dr. Cook? You have 20% fly ash replacement. Here's the original mix that maybe we use for ACI 211. Our specific gravities are here and our batch weights are here. So how do we go and we modify this mix to have fly ash in it now? Original one, as you can see, has just dashes in it. So how do we do? Well, ACI 211 uses sand as a filler. So, you know, what we'll do is we'll figure out how much cement and how much fly ash we're going to have. We'll do those calculations. And then we will adjust by using our sand as the filler. So we'll figure out how much volume the cement, how much volume the fly ash take up. And we already know our volumes for our sand and, you know, for our stone and water and air. So we'll just take that out. So, you know, 27 minus everything but the sand. And whatever that number is the sand volume. So we use the sand to balance it out to equal 27 so it yields properly. So step one, so if you have 20% fly ash, so you're going to do 564 because that was our total cementitious material times 0.2, which equals 112.8 pounds per cubic yard. So this 564, just kind of communicate, this was our original cement content. So that's what I refer to as the total cementitious material content. So cementitious material, that includes, you know, Portland cement, fly ash, slag, any of the SCMs, that total together. So step two, let's calculate the cement content. So we have 80% is going to be Portland cement. So 564 times 0.8 equals 561.2. If you add up 561.2 and 112.8, that better equal 564. If you didn't, then you did something wrong. So kind of be aware of that. So we figured out pounds, how much weight we have, but you know, fly ash is actually lighter than cement. So, you know, we're dealing with 3.15 as a specific gravity for cement, but fly ash is actually different. It's like, you know, 2.52 in this case. So, you know, your volume is not going to yield properly if we don't adjust our sand. So I figured out, you know, the 451.2 is the pounds. So that 80% fly ash that we just calculated, we divide that by our specific gravity times our 62.4, which is our conversion factor to get it from pound or from weight to volume. So 2.3 cubic feet. And then for fly ash, let's figure out the volume. So 112.8 pounds per cubic yard divided by our specific gravity times that 62.4, which is again our conversion factor from pounds to weight to volume. So that is 0.72 cubic feet. So if we add up, you know, we just calculated 0.2 and the 0.72, sorry, 2.3 and 0.72. And we already knew our coarse aggregate and our water and our air from that. Those were, you know, given in our example problem. So if we add up this entire column, that'll be 19.6 cubic feet. So how to figure out how much sand you need? Again, it's the filler. So anything left over to make it yield. So 27 cubic feet, you know, is in 1 yard of concrete. So 27 minus the 19.6 equals 7.40 cubic feet. So that's how much fine aggregate we're going to have to use. So how much weight is that? Well, 7.40 times 2.6 times 62.4 is, so 1,200 pounds of 1,200 pounds of fine aggregate. So here's our original, then our modifieds here. So if you look, this is 80% Portland, 20% fly ash. So if you add these two numbers up, they better equal 564. You did something wrong. We left our stone the same. We left our water and our air content the same, and we used our sand as a filler. So since fly ash is a little lighter, it's going to take up a little bit more, so you don't have to use as much sand. So you took out about 20 pounds of sand, which is almost nothing. But, you know, to properly yield, you have to go through these calculations.
So weren't you saving some money with the fly ash though?
Yeah. So this may be $130 per ton, and this may be $30 per ton. So you save a lot of money by using fly ash. You know, so it's quite a bit. I mean, we're dealing with stone and sand, which, depending on how far you got to drive, depends on, you know, we're dealing with maybe $15, $20 maybe. It just depends on where you got to travel to and from. But just to buy a rock or sand at that quarry, a lot of times like $5, $10. But to drive it to where you're at, it may be, you know, I've had some places where I paid literally $5 for the rock, but I paid $350 to get the rock delivered to me. So, you know, you just got to be kind of aware, you know, for a dump truck load. So this is pretty much dirt cheap. You know, these are really cheap, but cement and the fly ash. The cement's the most expensive, so you really want to use that fly ash when you can. So that helps you be competitive. So that's kind of how you incorporate this. So if we use, instead of, we use 20% flag or fly ash, but if we had slag and it was at 50%, you go through the same math, but you're going to have a different specific gravity, and your weight numbers are going to be divided in, this number in half. So if you're using 50% slag, and you're still going to use your sand as the filler. So let's talk about water reducer. So water reducers, the most common admixture used in concrete. Water reducer, air entrainment, they're the two most used. So we already incorporate air entrainers into our volume. We don't really talk a lot about air entrainers or water reducers or anything because your yield calculations are so small. So imagine, for the most part, when we talk about water reducers, air entrainers, the amount of weight that they contribute to our yield is maybe like a pound out of 4,000 pounds per yard. So they're like nothing. You don't even notice the decimal difference really. Now accelerators, if you're using 3% calcium, non-calcium accelerator, that's 3% of the volume. So you need to calculate that. You need to calculate the pounds. But whenever you're dealing with a water reducer, you really, for the most part, unless you're using a lot, you really don't need to calculate it for the yield because, and it's really common for people to not have that as part of their calc. But I'm going to go through a little bit of it just to kind of show you. It is important to actually properly yield. So what I'm trying to get at is when we deal with the water reduction. So normal water reducer, maybe 5 to 10%. The mid-range is 6 to 8. And then a high range is 12 to 30%. What does it mean? What does that water reduction mean? Anybody want to guess? So if you use a certain amount of a dosage, the recommended dosage, you can actually reduce the amount of water in your design mix completely. So that's what we're going to go through an example problem. So if we're using, say, 3 ounces of a mid-range, and that admixture company says, hey, for this mid-range at 3 ounces, you're going to have 8% water reduction. So how do we reduce the amount of water in this mix if we're going to use a water reducer? So how does that work? And again, our specific gravity may be something like 1.18 or 1.26 for a water reducer, and they're very, very light. They're almost like water. In fact, most of the ingredients are water. Is the biggest ingredient. So when you want to calculate, figure out for changing up your basic ACI 211 mix design, you're going to use the same. If we're using this original mix, basic air and train mix, you're going to have the same amount of cement and rock, and then our air for our air volume is going to be the same. But we're trying to modify how much water it is. We're trying to figure out how much sand we need to add to get there. Oop. Forgot to move that down. So if we do step 1, which is our water content. So we have 250 pounds of water times 92%. So we have 8% reduction. So I just said 1 minus 0.08. So we can figure out, okay, we need 92% of the water that was original. So 0.92 times 250 is 230 pounds of per cubic yard of water. And then our second part is if we need to calculate how much water reducer we have in our mix. So we're doing 3 ounces per hundredweight of cement. So we take the amount of cement we have, which is 564, times 3 divided by 100 pounds of cement. So this is another way of doing it. So I divide it out here, take 100 pounds out of that 564, so 5.64 times 3. So 13.92 ounces per yard. So that's actually what you batch that admixture at per yard. It's important to realize 16 ounces for this admixture is about a pound. So like I said, for this water reducer, it's pretty close to 1 pound is what it's going to equal, which is extremely low volume. So we don't typically incorporate that into the yield calculation. You can, you're more than welcome to. It's just in the field, it's not as common to incorporate it. If you get very precise, you're more than welcome to. With accelerators, we'll go through that on another day. So our volume of our water now. So we got our 230. So 230 pounds of water divided by 62.4 to convert from our specific gravity of water is 1. I could have put 1 times 62.4, but I didn't. So 230 divided by 62.4 equals 3.69. So a little bit less for water. So then your next step is you want to figure out how much sand you have in your mix. So you are going to take, your cement was given, your coarse aggregate was given, and your air was given. So we're just modifying how much water was in our mix. We're just going to neglect the very, 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 very small amount of water reducer, because it's probably 0.00001 or something for the cubic feet. So we're just going to neglect it. So when you add up this column, it comes out to be 19.14. So 27 minus 19.14 equals 7.86. So 7.86 cubic feet is the volume. So you can go back and do your calculations for weight of your fine aggregate would be 7.86 times the specific gravity of the sand, which is 2.6 times 62.4, which gives you 1275. So if you look back at this and we say, okay, well, so what did we do again? That our original ACI 211 mix design here. We modified the amount of water that was in our mix. So 8%, we're able to reduce the amount of water that was in our mix. And then we added about 55 pounds of sand to get it to yield properly. That's all we did. Okay. So very little sand, but that's how we get our mix to yield properly. So let's kind of switch gears a little bit. So this was something that I had whenever I first started doing mixed designs. I was able to get on a project one time, and it was with a new company. They just started making concrete. Nobody knew anything about concrete other than it was gray and it cracks and it's hard to still. You can't still concrete, it's really hard. No one ever cares about someone going out and stilling a sidewalk. It's really hard to do that. And so I said, Dr. Cook, we need help. We have no mixes at this brand new plant we just paid all this money for, and we just need mixes. How do we design our mixes? We need you to come and just design mixes. And if you know very much about ready mix operations, they have hundreds, if not thousands, of mixes in their computers. So, they have nothing. They have no historical data. I mean, nothing. So it's kind of a really cool opportunity for me to go out and just design mixes and then have them trial batched and measure them just to see what exactly is going on. So in essence, they needed mixes that ranged from 3,000 PSI to 6,000 PSI, because that's the majority of concrete. It's either not air entrained or non-air entrained, and it was 3,000 is usually your minimum. 6,000 is usually the maximum that people will order. Every once in a while, you have people order something different, and then you just design a new mix. But to get people set up, that's kind of how you do it. And you do about every 500 PSI. So 3,500, 4,000, 4,500, you go all the way up to about 6,000. So what I did was I said, okay, well, let's go ahead and just make some mixes, make them very similar. And like you saw with adjustments with the sand, just make slight adjustments with the sand, have different water cement ratios, because that's the number one change in the strengths, this water cement ratio. So I started out with like a 3,000 PSI mix. So I had a very high water reducer, or very high water content. And then I started lowering the water content and increasing the cement content to get the workability I needed. And so this is kind of what this is compressive strength versus the water to cement ratio. So, one thing that's really cool is you go out and you make somewhere between 3 and 5 mixes with this different water cement ratio. You can actually come up with a linear graph like this. So this is called a 3-point curve, is what they call it in the construction world. Linear algebra. We'll go and we'll just make a trend line. You can even have an equation and tell you how close to that line is, have an R square valued. But anyways, so you can take, and this is for 28 days. You can kind of guess where your strengths are at, where the water cement ratio, and you can go through and say, okay, so I don't have any data whatsoever, so I need to be at least 1200 PSI as a safety factor. So you can go through here, figure out, okay, where do I need to be at for 3000 PSI? Okay, well, I need to be at 3000 PSI plus a safety factor, come over, okay, there's my water cement ratio. Let's do on my next one. So I need to be at 3500, safety factor, come over, do same thing, you know, all of it, keep going up. So 5000, safety factor, come over. And you can go through and actually design your mixes. So this is what I did. I started out with a basic 3000 PSI mix, very similar to what we've been using. I put gallons in a lot of stuff I do because that's how you batch. So 8.34 pounds is in a gallon of water. So 8.34 pounds. So if you take that 304 divided by that number, you're going to get about 8.34 pounds. So that's what I did to get from pounds to gallons. 304 divided by 8.34. Just a little FYI. Sacks of cement, I think we've talked about in the past, but there's 94 pounds in one sack of cement. So if you take 470 divided by 94, you're going to get 5 sacks. So back in the day, that's how people designed all their mixes with, they start out with, like I say, a 5-sack mix, and then they would go up from there. So that's what I did here, was I took, and I changed my water to cement ratio, and I added a sack of cement every time. And I went up. So that's why, if you're ever curious why a 3000 PSI mix is a lot more expensive than, say, a 5000 mix, because you have so much more cement in there. So, but this is a really common mix designs if you actually compare them for people to actually go through and design. So again, so for 3000 PSI, you're going to have, and you compare it to the, say, 3500, you're going to have a lower water cement ratio. As your strengths get higher, you're going to have lower water cement, so you're going to have more cement. You're not watering down the amount of cement you have in your mix. And so that's the correlation with water and the cement. That's water cement ratio. And then what, if you noticed here, you have 1,800 pounds of rock, so it's uniform. That's what ACI 211 tells you. But if you look here, you have about 1,360 for sand. Down here, you're getting to be almost down into under 1,000 pounds. So what happens a lot of times when we start designing mixes at 8,000, what I have learned is all of a sudden, hey, you just don't have enough sand in your mix. So that whole thought about just making sand always a filler doesn't work out too well. So what I'll do is I actually use both of these. So I'll just take weight off both the whole time, and it actually works out really well. So that way you don't have just a very low number, you have something that's kind of in the middle. But that's just what I do when I design them in the field. ACI 211, this is how they would tell you to design a traditional mix. Does that make sense, what I'm getting at? This is how you go out in the field and design if you were a new quality control manager for a ready mix operation. That's how they would design it. And this is for non-air train. So if you did air train concrete, your numbers would look a little different here. So your water cement ratio, you'd obviously need, lower numbers. So you may be at 0.40 to get 6,000 PSI. So 3-point curves can be extremely important, can really help you out when you're trying to design mixes. So that's kind of when you order 3,000 PSI concrete compared to 3,500, and you're like, well, what's the difference? The difference is usually they're going to add a little bit more cement. They're going to take out a little bit of water to get their strengths. So what's another way, instead of adding cement, maybe you just take out some water and you add a water reducer. So that way you can reduce the amount of water. Maybe you make this 5.0, and maybe you can use, 3 or 4 ounces of a mid-range and get the same workability, and you still change this value without having to add more cement, so you can have more of an economical mix. And then maybe when you get to 4,000, maybe you add a much higher amount. Maybe you add 8, 9 ounces to still reduce the amount of water or cement, the amount of water you have in there. So you can still have this water cement ratio, but you're still at maybe 5 sacks. Does that make sense? So that's kind of pretty common for people when you start trying to make your mixes more and more cost effective, so that you're not going out and going, okay, well, 3,000 PSI mix is maybe, let's start off with $100. That's cheap, but maybe it's $100. Well, it's 105 here, and it's 110 there, 115, 120, 125. Use a water reducer, maybe instead of 105 here, maybe it's just 101. Does that make sense? Okay. So, trial batch method, I didn't have time to put all the steps down. But in essence, another way to design concrete is to just go out in the lab and start making concrete. So you may start out with something maybe ACI 211. You may start out with something that you just kind of came up with. You start trial batching, testing the concrete, saying, did it meet the requirements? If it didn't, adjust the proportions, change your mix design up a little bit, re-trial batch it until you get to someplace where you feel pretty comfortable with that performance of that specific mix. And like I always say, trial batching. It may look great on paper, but you have to go out in the lab, go out in the field, and actually figure out with that new mix how it looks. So I always tell people, when you design in general, how you get real experience is you go out and you look at your designs. So when you design a concrete mix, go out and actually see how it looks when it's being placed, when it's being finished. Not just the cylinder breaks, not just the test results over here, but maybe in the lab, but see how well people can actually use it. And then go back years later just to look at it. Whenever I was a concrete finisher, I'd go back 10 years. I remember going on jobs with my dad, 30 years ago, he poured that. And we'd go back to it just to see, hey, there was this design this is what happened. I just want to see how it's still working. And you go back and look at it. And this is really, you know, back in his day, you didn't really have, you know, degrees like this. So, you know, he barely had a high school education. And so he'd go back and we would look at how we did stuff differently in the field then compared how it was performing now. And so it really gave us a lot of good insight, especially when you build something, you look at the drainage. Maybe you do a parking lot or a mini storage complex, and you see how that water flows, even though you did all the gradations, all the grading right, according to the drawings, just to see that water flow and actually drain properly, you can really learn a lot. So just kind of want to be aware of that. Is there any questions? Okay, so we have homeworks again, and this will be the last of a lot of the math. Then we'll have another assignment that'll come out next week. That's over a lot more of the testing. So you'll kind of have one homework that's kind of mirrors some of the stuff you had in your ACI field grade 1 quizzes that we've had in our lab. And we'll have next week we'll have PowerPoint over testing and stuff. So it'll be kind of cool going through some of that. I won't try to regurgitate all the information from our labs. So we'll go over secondary testing and stuff like that. So if you know, when you take a core, when you have to use a Schmidt hammer to figure out uniformity, using other secondary strength testing other than just compressive cylinders. So anyways, have a great rest of your week, and I will see you next Monday.